we have started to deal with the problem of vibration of diatomic linear lattice in previous lecture. And in the first part of that lecture, you have seen the deduction of a very important relation which relates the frequency of vibration omega and the wave vector k. And that very relation is called dispersion relation. So the first lecture was intended to find the dispersion relation, but we have not discussed that very important result in the first part of the lecture. And now today is the time when we will see the important points of discussion of this dispersion relation of the vibration of diatomic linear lattice. Okay. So I have mentioned here the final result which we have obtained in our first lecture on this vibration of diatomic linear lattice. You have seen, you can remember if you have watched my first video on this vibration of diatomic linear lattice, definitely this result will be in your mind, and you can see we have obtained the square of the frequency of vibration, that is omega square. That was found equal to mu times 1 over m plus 1 over capital M plus minus mu times a square root of this much, that is 1 over a small m plus 1 over capital M whole square minus 4 sine square Ka divided by m times capital M. Okay. You know the meaning of each and every term here. Here actually this mu is the force constant, okay, and a small m we have assumed this is the mass of the even numbered atoms of the diatomic lattice, and capital M we have assumed is the mass of the odd number atoms. And in our calculation we have assumed that this small m is smaller than this capital M. This was our assumption. You can take just opposite assumption too when you will consult a textbook. It is possible that in that textbook you find that capital M has been taken greater than this, capital M has been taken smaller than this small m. It is possible. But our calculation was based on the assumption that a small m is less than capital M. Now you can see here this sign of both plus and minus implies that actually for a given value of k there will be two values of omega square, because omega cannot be negative. So the two acceptable values can be obtained by taking this plus minus sign separately. So when you will take the plus sign, then you write the frequency by the symbol omega plus, and so omega plus square will be equal to what? That will be just equal to taking the plus sign here. Okay, so this is the expression for omega plus square. And similarly, when you take minus sign, then you get the expression for the another frequency, that is omega naught minus square, and that expression I have mentioned it here. Okay, I am not giving a reading because you can see this result. Okay, actually these two values of omega which was obtained in the previous lecture, actually this relation is known as dispersion relation because it relates omega with k. Okay, now when you will plot this omega in against of k, the graphical plot obtained I have shown in this very figure. In fact, it is seen that when omega versus k is plotted, we find that there are two branches, one corresponding to omega plus value, which is the upper branch. You can see I have shown in the figure here. This is the upper branch, and this is the graphical plot of omega plus in against of k. And this upper branch is actually called optical branch. And the another branch which is for omega minus that is the lower branch, this is called acoustical branch. Because why it is called optical and acoustical branch? Because the frequency of this optical branch is just in the range of the optical frequency, and this omega minus is in the range of acoustical frequency, that is this is almost of the order of frequency of the sound wave, and so this is called optical branch. Okay, and now we will discuss this dispersion relation and this diagram in very detail. Now let us see, when this k is equal to 0, then what are the values of this omega plus and omega minus? You can easily found taking k equal to 0 in these two results, that is in equation B and equation C. So when we will substitute k equal to 0 in equation B, we will obtain the value of omega plus, and putting k equal to 0 in equation C, we will obtain the value of omega minus for k equal to 0. So now let us found these two values. For k equal to 0, what will be this omega plus? You can see this value. When k is 0, you know sine 0 is 0, so this term will vanish, and the term inside the square root will be 1 over small m plus 1 over capital M whole square, and its square root will be simply 1 over m plus 1 over capital M. So this omega plus square will be equal to mu times 1 over m plus 1 over capital M plus mu times 1 over m plus 1 over capital M. So this is simply 2 mu times 1 over m plus 1 over capital M. And so if you want to find omega plus, which is supposed to be equal to omega 3, as I have shown in this figure, this value for k equal to 0, here is k equal to 0, and so this value of omega corresponding to this point, let us say A, represents that value of omega plus, which I have denoted by this symbol omega 3. But this omega 3 is equal to what? You can see this is found to be this much. Okay, this is 2 mu times 1 over m plus 1 over capital M whole square root. Okay, so you can mention it here. This is a square root of 2 mu times 1 over small m plus 1 over capital M and whole to the power half. Okay, so this is the value of omega plus when k is equal to 0. Now let us see what will be this omega minus for this value of k equal to 0. Again, this terms containing sine square ka will be sine square 0, and that will be 0. And the first term mu times 1 over m plus 1 over capital M minus second term will be minus mu 1 over m plus 1 over capital M, and both will be cancel out, and so after cancellation you can see that this omega minus will be simply equal to 0. So you can see in this graph that when k is equal to 0, omega minus is 0, but omega plus is equal to omega 3, which is equal to this much. Okay. Now when k is equal to plus pi by 2a or minus pi by 2a, then you will see that this omega minus will be maximum, but this omega plus will be minimum. Now we will actually discuss the frequencies of the two branches, that is acoustical branch and the optical branch, separately. So now let us see the important facts regarding the acoustical branch. Okay. When you say acoustical branch, then the lattice spectrum is described by the frequency omega minus, and you know that omega minus will be given by this equation C, which I have mentioned it here. You can see that this is the frequency defined in this equation C. This represents the frequency of the acoustical branch. So now we will see some of the important facts regarding this result. So again, if you take k equal to 0, as already you have seen, when k is 0, then omega minus is 0. I have just repeated the same fact here, that when k is 0, omega minus is 0. Okay. But when k is equal to either plus pi by 2a or minus pi by 2a, then what will be the value of this omega minus? As I have told you earlier, that at these values of k, in fact, the value of omega minus will be maximum. And what will be that maximum value? You can easily find. So let us see what will be the value of this sine square ka when you take k equal to either plus pi over 2a or minus pi over 2a. You know, sine ka, this will be sine k. At the place of k, I have written plus minus pi over 2a times a. Now this a and this a will cancel out, and you know sine minus theta is equal to minus sine theta. So this sine plus minus pi by 2 can be written as this is plus minus sine pi by 2. And sine pi by 2 is equal to 1. So this is plus minus 1. So when you will square it, that is sine square ka, that will be 1, and this is its maximum value. Okay. And when this will be maximum, then omega minus will be also maximum, because you can see this result, that when this factor last term will be at its maximum value, we will subtract maximum from this. Okay. And again I have to subtract from here. Okay. So when you will subtract maximum, you will get minimum, and when you will subtract minimum, you will get maximum. So in this condition, omega minus will be maximum, and what will be that maximum value? You can easily found by substituting sine square ka equal to 1 in that very equation C. So let us see omega minus square. What will be that? You have seen the result. The first term was mu times 1 over small m plus 1 over capital M, and minus mu times 1 over small m plus 1 over capital M whole square, and minus 4 sine square ka over m times m. But sine square ka is equal to 1, so this last term is minus 4 over small m times capital M. Okay. Now let us see. This is just like a plus b whole square minus 4ab. Okay. And you know this is equal to a minus b whole square. So for this we can write this is equal to 1 over m minus 1 over capital M whole square. And after taking the square root, this will be simply 1 over m minus 1 over capital M. So our result is mu times 1 over small m plus 1 over capital M minus mu times 1 over small m minus 1 over capital M. And so you can see from here that this mu over m will cancel out, this will cancel out, and the remaining term will be only mu over capital M plus mu over capital M. So this will be 2 mu over capital M. Okay. And so this omega minus which I have denoted by the symbol omega 1 in the dispersion relation curve, that will be equal to a square root of 2 mu by m. So you can see that at these two boundaries, here omega 1 is equal to root over 2 mu over capital M. Okay, and here also this omega 1 is equal to root over 2 mu over capital M. Okay, this is the maximum value of the acoustical branch. Okay, maximum value of the frequency of acoustical branch. Okay, actually here the first Brillouin zone defined by the k values lies in the range between minus pi by 2a to plus pi by 2a. And if at the boundaries of the first Brillouin zone, k is equal to what? This is pi over 2. I have neglected the minus sign. Then this is the maximum value of the wave vector k in case of the first Brillouin zone, or the value of k at the boundaries of the first Brillouin zone. And you know, lambda which is wavelength, this is equal to 2 pi over k. Okay, so when k is maximum, what will be lambda? Lambda will be minimum. So if you want to find the smallest or minimum possible wavelength of this first Brillouin zone, then what will be that? You can easily find that the lambda minimum will be equal to 2 pi over k maximum. But k maximum you can see is pi over 2a. So lambda minimum is 2 pi over 2a. Now this pi and this pi will cancel out, and this is equal to 4a. So the smallest possible wavelength of first Brillouin zone is equal to 4a. Here one thing is very remarkable. When you have studied in my previous video the concept of vibration of monatomic linear lattice, then you have seen that actually the first Brillouin zone lies between minus pi over a to plus pi over a. This was the boundaries of the first Brillouin zone in case of monatomic linear lattice. But here in case of diatomic linear lattice, you are seeing that the boundaries are minus pi over 2a and plus pi over 2a. Why? Why this difference is here? Because you know, actually in finding the boundary of a Brillouin zone, we have to see in this case not the neighboring nearest neighbor distance. Actually here you have seen that there are two types of atoms. Okay, and if this is 2n, this is 2n plus 1, and this is 2n minus 1. Its mass is a small m, its mass is capital M, its mass is capital M. And the distance between two successive atoms is a. This will be a. Okay, but the periodic repetition of the same atom it takes place for a separation of 2a, not a. You can see the distance between this capital M and this capital M is not a but 2a. And that's why in this case the first Brillouin zone lies between minus pi by 2a to plus pi by 2a k values. Okay, so I have mentioned it here that this difference in range is due to the fact that it is determined not by the nearest neighbor distance but by the periodic repeat distance, which is in this case equal to 2a. I think we have clearly understand why this difference between the range of the first Brillouin zone in case of one-dimensional monatomic linear lattice and the diatomic linear lattice. Okay, so I think you have clearly understand. Okay, now I have mentioned here two equations, but these two equations have been derived in the first part of the lecture. So I have mentioned it here. You can see the first part of my lecture on this vibration of diatomic linear lattice. You have obtained these two relations. The first relation says 2 mu minus omega square times small m times a is equal to 2 mu b cos ka. Here you know this a is the amplitude of the vibration of this small m mass, and this is the amplitude of small m, and b is the amplitude of vibration of this capital M. We have seen earlier. Okay. Now from these two results we can relate the amplitude of vibration of the two types of atoms. So if you want to find the ratio of the amplitude, that is b over a, then let us see equation 3a. In accordance with equation 3a, what will be b over a? You can see from equation 3a, b over a will be equal to this much. This will be 2 mu minus omega square m divided by 2 mu cos k. But when you will find the same ratio, that is b over a, from this equation 3b, then that will be equal to this much. This will be, you can see the equation, 2 mu cos ka divided by 2 mu minus omega square capital M. Now, if you consider a situation that k is much smaller than pi over 2a, in other words, you can say that if k is tending towards 0, then actually taking cos ka tending towards 1 minus k square a square divided by 2, not equal to 1. I have taken the second term 2 for a good approximation. Okay, so when you will take this and apply in this result, that is in equation 4, then you will get this simple result. I have not actually done the algebra here, so you can remember it, but you can do it yourself, that when k tends to 0 or k is very small in comparison to pi over 2 and taking cos ka equal to this much, then it is found that b over a is almost equal to 1. It means in this condition, both the atoms, that is even numbered atoms and odd number atoms, that is atoms of mass m and atoms of mass capital M, both vibrate with almost equal amplitude. Okay, equal amplitude. But this fact is not true when you say that k is now increasing, k is large. When k and omega increase, actually then this b by a also increases. It is not equal to 1. Okay. Now you have seen that the highest value of omega minus is denoted by the symbol omega 1 is equal to this much. So when we consider that omega minus is at its highest value, then what will be this b over a? Let us see. When you will take this result b by a, see here, this is equal to 2 mu cos ka and divided by 2 mu minus omega square capital M. But now at the place of omega square we will write this much. Okay, this much, and this is 2 mu divided by capital M. and times capital M. So this M and this M will cancel out, and 2 mu minus 2 mu will be what? That will be 0. And so when you will divide this 2 cos Ka by 0, here is non-zero, and when you will divide by 0, you will get infinity. So B over A in this condition will be infinity. Mark it, I have used the second expression for B by A, not the first expression here. Okay. So in this condition, B by A is infinity. But can you say, if B by A is infinity, what is A? A will be 0. So amplitude of vibration of the lighter atom in this case is 0. And if amplitude of vibration is 0, what does it mean? What it physically implies? It implies that the lighter atom will not move, it will not vibrate. So if you consider the frequency of the acoustical mode at its highest value, in that very condition, the lighter atom almost remains at rest. Only the heavier atom will vibrate, the lighter atom will not vibrate. Okay, this is a very remarkable fact. So this all these facts were related to the acoustical branch of this lattice vibration. Now we are going to see the important facts related to the that was related to the acoustical branch. Now we are going to see the important facts of optical branch. We have seen that the optical branch of the lattice spectrum is described by the dispersion relation given by omega plus square equal to this much. This is mu times 1 over small m plus 1 over capital M plus mu times a square root of this much. That is 1 over small m plus 1 over capital M whole square minus 4 sine square Ka over m times m. Okay. Now let us find again the value of this omega plus square when K is equal to plus minus pi by 2a. That is, we are now going to find the value of the frequency of optical branch at the boundaries of the first Brillouin zone. Okay. Actually, in this case, you will see that the frequency of the optical branch is minimum, is at its lowest value at the boundaries of the first Brillouin zone. And what will be that? For this, again, you know, when K is equal to plus minus pi by 2a, then this sine square Ka, sine square Ka, this is equal to what? Sine square Ka is equal to 1. You have seen earlier. So our expression for omega plus square will be equal to this much. This is mu times 1 over m plus 1 over capital M plus mu times a square root of 1 over m plus 1 over capital M whole square minus 4 over m times m. Again, you can see this is in fact 1 over m minus 1 over m whole square. Okay. And so this result will be mu times 1 over m plus mu times 1 over m minus 1 over capital M. Here this 1 over capital M term will cancel out and your result will be 2 mu over small m. And so this omega plus, which is denoted by the symbol omega 2 in the dispersion relation curve, that will be equal to a square root of this much. So you can see the dispersion relation curve here. See the dispersion relation curve. This is your curve. Here omega 2, what is omega 2? You have obtained that this omega 2 is equal to a square root of 2 mu by a small m. 2 mu by a small m. But you know, our assumption is a small m is smaller than capital M. So the page has been turned, but this will be just okay, don't worry. Let us see it here. Since small m is smaller than capital M, let us see. So definitely this 2 mu by a small m square root, this will be greater than a square root of 2 mu by capital M. Okay, and so you can see the highest value of the frequency of acoustical branch, that is omega 1, and the lowest frequency of the optical branch are not same. Okay, but this omega 2 is greater than omega 1. Okay, so there is a frequency gap between these two branches. Optical branch and the acoustical branch are separated by a frequency gap which is equal to, in fact, delta omega, and that delta omega you can see will be equal to omega 2 minus omega 1. Okay, there is, so I have, you can see in this figure I have written here forbidden frequency gap. Actually the frequency which lies between omega 1 and omega 2, that cannot be excited in this lattice. It means that frequencies are prohibited frequencies. You can excite all those frequencies which are from 0 to omega 1 and from omega 2 to omega 3. But the frequency lying between omega 1 and omega 2, that cannot be excited. So those frequencies are called forbidden frequency. This is a very important fact, and this is due to the periodicity of the lattice. Okay, so this is just like the band gap, energy gap. Here is frequency gap. Okay, let us see now. Now again you can see in this case, okay, when k is equal to 0, then what will be omega plus? Actually I have denoted in that figure with this value of omega plus by omega 3, and you can easily find it by substituting the value of k, that is k equal to 0, in the expression which I have mentioned it here for omega plus. You can see this is the value of omega plus. Sorry, this is omega plus. So when you will take k equal to 0, this last term will vanish and the first term and the second term will be same, so both will be added, and that will be 2 times mu into 1 over small m plus 1 over capital M. Okay, so this and whole square root. So this value of omega is equal to this much. This is a square root of 2 mu times 1 over m plus 1 over capital M. Okay, now when k is equal to 0, then what will be this ratio b over a at the value k equal to 0. So you can see the expression for b over a in this equation 4, but here we are going to found the value of b over a when k is 0. You know, when k will be 0, cos ka will be 1 because cos 0 is 1. So taking cos ka equal to 1, now you can write the value of b over a. B over a. Let us see. So b over a, this will be equal to 2 mu minus m omega square over 2 mu, and that will be equal to 2 mu over 2 mu minus m omega square. Okay, but you have seen that when k is equal to 0, then omega is equal to omega 3, that is, which is defined here. So now let us substitute the value of omega in this result. In the first expression, let us see in RHS. So B over A. So you can see I have divided this numerator by 2 mu separately. So this will be 2 mu over 2 mu, okay, and minus m omega square over 2 mu, okay. So this 2 mu will cancel out and that will be equal to 1. So I have written here 1. And m over 2 omega and omega square, but when k is 0, then omega is equal to omega 3 and that omega 3 is equal to this much. So let us substitute it. So when we will square it, the result will be 2 mu times 1 over m plus 1 over capital M. Now this 2 mu and this 2 mu will cancel out, and let us multiply by this small m to the terms inside the bracket. So this will be 1 minus 1 minus small m by capital M. Now this 1 and this 1 will also cancel out, and so you will get B over A equal to minus small m over capital M. Okay. And if you will take m equal to m, if you consider that there is a diatomic lattice, the masses of whose both atoms are equal, then what will happen? Then B over A will be equal to minus 1. So what this first result actually implies? Actually this first result implies that when k is equal to 0, actually in that condition both the atoms of this lattice in optical branch will vibrate with vibrate and in opposite directions. This minus sign actually implies that the vibration of both the atoms takes place in opposite direction. As you can see in this figure, actually this hollow small sphere and this solid sphere denotes the two types of atoms. So if one atom is moving up, then the another is moving down, you can see, okay. So this indicates that the two atoms moves in opposite direction. And since B over A is equal to minus m over capital M, but you know this A is what? This is the amplitude of vibration of small m, and B is the amplitude of vibration of capital M. So here you can see the amplitude of vibration is actually the inversely proportional to their masses. It means the heavier atom will have a smaller amplitude, and the lighter atom will have larger amplitude. Okay, but if both atoms are of equal mass, then B is equal to minus A. It means in that condition both atoms will vibrate with same amplitude but in opposite direction. Okay. Now, as I have told you that an important feature of this lattice vibration is the forbidden band, because you can see that there exists a band frequency between these two branches for which the frequency cannot be excited. As I have told you, the frequency that is omega 1 less than omega and this less than omega 2. This frequency which lies between this omega 1 and omega 2, that cannot be excited in this lattice. So all those frequencies lying between omega 1 and omega 2 are known as forbidden frequencies. Okay. So this band is called forbidden band, and the width of the forbidden band you can see is given by omega 2 minus omega 1, as I have shown in the dispersion curve, and omega 2 minus omega 1, and omega 2 minus omega, and omega 2 is equal to what? Omega 2 you can see is equal to, omega 2 is equal to this much, and omega 1, you can see what is omega 1. Omega 1 is equal to this much. So when you will subtract omega 1 from omega 2, this square root of 2 mu can be taken as a common factor, and so this result will be a square root of 2 mu times 1 over m minus 1 over capital M. This is the bandwidth, this is the frequency gap. Okay, but when the masses of the two atoms are equal, then what will be this value? You can see then this 1 by m and small m and 1 by capital M will cancel out and your result will be 0. So actually there will be no forbidden frequency gap in case the diatomic lattice has two atoms of equal masses. In that condition there will be no frequency gap. But if the masses of the two atoms are different, there will be a frequency gap. This band gap of frequency is a very important fact, and this is of much importance in dealing with the physical problem. Okay, so I think you have clearly understand the discussions on this dispersion relation and what are the basic feature of the two branches of frequencies. Now it has been clear to you. Okay, thank you very much.